So far, we now see how to compute this one fast. And immediately it implies that you can compute this one fast. SE hierarchy. Now we're gonna try to do this fast. And it will imply other stuff. So once, by the end, maybe by the end of next week, hopefully you see how to, you should convince yourself that you can do everything here fast. Yeah. Okay, so let's look at next goal, make this fast. Okay. Okay. It's likely that I will need to continue this tomorrow too, but yeah. Just to recall, right? Expanded decomposition. You have a graph, a node weighting, and phi, and you want to compute a cut C such that the cut size is something like phi log n times the node weighting size, and node weighting is expanding. Okay, so you find a cut so that each component here is expanding. A is expanding in each component. Okay. Now, the goal is to basically do the same thing, but with some relaxation. What's relaxation? Well, instead of phi expanding, you don't get exactly phi. You get a bit worse by log square factor. And the running time is something like MaxFlow, Polylog calls to MaxFlow again. Okay, so let me motivate the algorithm a bit, right? We see the algorithm before. This is a not fast algorithm, which is just to say that as long as A is not expanding, then there is a sparse cut. Cut that. There is a sparse cut. Include that cut to your answer and repeat until you cannot do. If you cannot do it, then A is expanding. Like this. Keep finding sparse cut. And then you look at this component. Is there sparse cut here? Look at this component. Is there sparse cut here? And repeat. Right? Okay. I can rewrite the same, this is the same algorithm, just rewritten. I can say that, okay, given G, A, and phi, just if A is already expanding, I just return. Nothing to do, right? And then otherwise, I find a phi sparse cut. If it's not expanding, there is a sparse cut. Then what I return is I just return this cut, right? This is edge crossing S, the cut. And I recurse on both sides. Are you convinced that this is just the same algorithm? Right? I just recurse on G induced by S and the node weighting induced by, on the intersect S, G induced by the complement and the node weighting on the complement. Just the same algorithm. But we know that this is not fast for sure. Why is that?
Finding sparse cut is NP hard.
Exactly. Just check if there is a sparse cut or not. It's just NP hard. So not great. But we know how to relax this and make it fast now. What is that relaxation?
We can use a flow instead of. We can check whether we can route a phi by log n flow, and then we can use some LP to.
Yeah.
In polynomial time, we can do it basically.
Yeah. In poly time, you can instead say that, we say that either this is phi expanding or you find phi log n sparse cut. Or in other words, I can just say that conclude that A is file overlog expanding or file sparse cut. So the log n can be here or can be here. Just yeah. So that's polytime. But now actually we know how to relax this a bit further and make it almost linear time. How to do this? Like to check if there is a file sparse cut or conclude that A is like close to file expanding. Just this subroutine, we can do it fast now. Why is that?
With the max flow stuff?
Yeah. With what?
The cut. I don't remember the name, but like we either have the flow where we get some cut separating.
So that's not quite like that is just like one call to max flow, right? One call to max flow, you have the source and the sink and you get some cut. I'm not sure is that what you mean, but there is some more precise way to say what can we do. So I claim that if I just change to this goal, I just check if like either say that A is phi over log square expanding or else I find a phi sparse cut. Here I can do fast in almost linear time. Why? Why is that? What is the algorithm to do this? I let you review things, maybe have a look in 2 minutes. Yeah. Like in our previous lectures. Yeah.
Like the cutter expand from the doing like a patching game with the max flow to between the AI and DI each time.
Yeah. This is really like our first application of cut matching game when we don't do deletion or transferring vector, right? So let me point out to the lecture. 1 sec. Wait. Here, right? we know that like given any graph and node weighting and phi, we can either find a phi sparse cut with respect to node weighting, or say that the node weighting is expanding in G. How do we do this? We just run the cut matching game, the standard version on this node weighting. Okay. That's like basically give us like approximate sparse cut algorithm. We either like say that, okay, there is a phi sparse cut or there's no phi over log squared of sparse cut. So that's fast. Okay. Okay. So this is like fast. You can just use Polylog Minimax flow. Okay. But even if this thing is fast, the whole recursion might be still slow. Like the whole thing might still take like at least mn time. Do you see why that can be the case? What's wrong? So what's wrong is here. What's wrong is that the cut that we find might be tiny. Like, might be like just tiny. And then we need to recurse on the big side. And then we cut again. And this might happen n times, right? Might happen like an order of n times. So even if to find the cut, one cut, it's just linear time, you might need to repeat working on the big graph, essentially of the same size, close to n time. So the total time could be still mn. So like because the recursion depth is like of size n. Okay, so what if I always find a balanced one? Okay. So what will happen here is look like, suppose that the sparse cut that I find looks like this. And when I recurse on both sides, it looks like it's kind of balanced. Okay. What's the time here? It should be now almost linear. Why? Like just because like the total time on like the recursion depth is like log n because it's balanced. Like the cut is balanced. So let's say you split the graph in a balanced way, so the recursion depth is log n. And you know that the total time that you're going to spend for each level is near linear. It's almost linear because like in one problem here, you spend almost linear time. Now you recurse here. This is like almost linear on this side, almost linear on this side. So in total, it's almost linear on the whole graph. So the total time per level is almost linear. Okay. So in this case, you're going to get almost linear time, if that's the case. But that's still a problem, because what if there is no balanced sparse cut? That can happen, right? It can be the case that when you look at balanced cut, they are not sparse anymore. They are kind of expanding. They can have a lot of edges crossing. So what to do here? Right? That's the question. And basically, this is a subroutine that I want you to have in mind. Either find balanced sparse cut or identify giant expanding set. So the message is this. If there is no balanced sparse cut, then something nice must happen, actually. So what's nice is that there must be giant expanding set. So in picture, it looks like either there is a balanced sparse cut, or you cannot really cut it. Like there is like a big expanding set here. And that kind of makes sense because the only reason that you cannot find balance and sparse cut is because there is some big expanding set that you cannot cut through. Okay? So that makes sense intuitively, but let's prove this formally. So the claim is that given any graph, there exists a vertex set S. It might be empty, such that first of all it's sparse. The cut, like if you think of S as non-empty set, it's a sparse cut. The cut size is most phi times A from minimum of A from both sides, minimum of the node weighting. So it's a sparse cut with respect to A. But either of these cases will happen. Either it's balanced. So the size of A is basically like constant factor of the whole A. The size of S is constant factor of the whole node weighting. Or maybe S is small. But if you look at the complement of S, in this case, draw it. S is tiny. But now if you look at V minus S, the node weighting on the complement is already expanding in the complement. This just means that this part, right, is already expanding. Like the node weighting here is expanding in the complement, in the graph induced by the complement of S. Is the statement clear? So the proof is actually simple. Okay, but yeah, what we say is just that like you either have a balanced sparse cut, or okay, you might find like tiny sparse cut, and the rest is expanding. It's basically phi. It's basically phi expanding, but a bit worse by factor 4. This factor 4 and 5 here is not something that like I optimized. By the way, you can make it a bit better, but it will not be exactly phi. Okay. So the proof is just, let's say that I let S to be the most balanced sparse cut. What do I mean? I mean that, like, let's say that S is on the like less than half, and this just means that it's sparse, right? The cut size of S is less than phi times AS. So this is just to say that it's sparse cut. It's a phi sparse. But I want it to be the most balanced one, meaning that this is maximized. So like, if there is like this sparse cut, and there is like another cut, then I take this one. Just make it the most balanced, but it should be like on the smaller side. Okay. So if S is just this thing, then this is not. Then it's not quite balanced because this part is small. So I just, take the one that is most balanced. Okay. So if S actually is the most balanced one, and if indeed is quite balanced, then we are done. Because it's really just a balanced sparse cut. Okay, so what we need to prove is like, suppose that even the most balanced one is not balanced. Like, suppose that this is false. Then we want to prove that something happened. Okay. Suppose that this is false, actually that the size of S is actually small. Then I want to prove that the complement is expanding. This is what we just want to prove. Okay. But that's not clear yet. but I want, like, are you convinced that if we prove this, then we are done? Right? Literally just say that, like, just give this thing. Like, we get that either this is the case or S is small and the complement is expanding. Okay. Good. Okay. So let's say that this is not true. Suppose for contradiction that is not true. Then there must be a sparse cut in the complement. So, okay, I have this guy, I have S. And let's say that this part is not an expander. It's like the node weighting is not expanding in this graph. So there is another cut. Another cut, maybe here, T and U here, such that this cut TU in the complement is sparse in the complement. So that is the edges between T and U. This is what I mean by, this is just the cut size in the complement. Edges between T and U here is small. How small? Like at less than 5/4 times the like minimum of the node weighting from T and U. Okay. So when I look at this one, then I just claim that S union T, like, so, okay, maybe I draw. Yeah. This is S, and let's say this is T. Okay. This is like phi sparse. This is like a 5/4 sparse in G complement. This is in G. Now I claim that like this union, this cut, is just gonna be another phi sparse cut, but now more balanced. So that would be if that's the case, then we would be done, right? That would be a contradiction. Okay. So let's see why this is the case. Why like the union here must be phi sparse and more balanced. Well, what we know is that like it's more balanced for sure because like T and maybe I just So assume that like the size of T is less than the size of U. Then what you know here is that like the cut size here, right, is at most phi times A of S, because S is phi sparse plus this part. Like this part is at most phi times AS, and this part, this is at most phi/4 times AT. Just because this is phi/4 sparse. Okay. And then well, this is less than both of these things. Okay. So the first, this thing is less than phi times A union T. That's easy to see, right? This is easy to see. What about like why this is less than? But what about this one? What about why this is less than A phi times AU? That's less easy to see, but it's like here. Like first of all, you know that AU need to be quite big. Why is that? Well, like because S here is less than A/5, right? So this part is at least 4/5 times the whole A. But then u is more than half of t. Like u is more than half of this one. So the size of u is at least half of this thing. So it's at least 2 over 5a. Okay. So u is of at least 2 over 5a. S is at most 1 over 5a. So as is at most 1/2 of u. 1/2 of au. Okay. But if that's the case, then like this thing is less than au over 2. This thing is less than au. So it means that this thing together, actually, sorry. If you kind of look at this thing, right? This is less than au over 2 plus au over 4. So this is less than au. Okay. All right. So it's in this 5 sparse, but it's more balanced. Why it's more balanced? Because, yeah, this is more than AS for sure, and this is more than twice of AS. So both sides of this cut is just larger than the size of S. So it's more balanced. So yeah, like that's a contradiction. So we get this one now. And this is actually true for like we either get there is always balanced sparse cut or giant expanding set. Okay. And this is gonna be true too. Like if you just adjust parameter beta to be instead of 1/5 is anything smaller than beta. Yeah. And okay, so now what we're gonna do next is this is just existential proof. We're gonna show that we can actually do something like this fast. And if we can do something like this fast, then we get expanded decomposition kind of fast. So we do that tomorrow. Right, see ya. Yeah.